Hi everyone, my name is Chiranjeevi, and in this video we will continue our discussion on structural design patterns, and in this video we will take a look at bridge pattern. So following the pattern in the previous videos, we will discuss what is bridge pattern, we will take a look at the definition, then we will take a look at the problem it is trying to solve, the UML diagram, and a code example. So let's quickly dive into the definition for the bridge pattern. So this is the definition for the bridge pattern. It's a structural design pattern that decouples an abstraction from its implementation so that two of them can vary independently. Well, comparing with the other design patterns, this bridge pattern specifically was more complex to understand for people who are starting out in the design patterns. And if you look at the definition, there are quite a few points which you should note what this pattern is trying to do. So what it says here is bridge pattern decouples an abstraction from its implementation so that two of them can vary independently. So here, what we need to identify is what's an abstraction and what is the implementation of the abstraction. So after identifying what kind of abstraction and what kind of implementation are there in the code base and what are we actually trying to decouple, then only we can understand what this bridge pattern's intent is, what is it is actually trying to do. So to understand this pattern, first we will take a look at some of the uh, examples, then we'll take a look at the UML diagram of the bridge pattern and exactly try to find where actually the bridge lies in the UML diagram and in the bridge pattern. So let's take a look at some of the examples here. Okay, so this is the first example we will discuss as a problem which actually gives us a way towards, or which actually tries to bend us towards the bridge pattern. So these kind of scenarios which I'll discuss in this video are the actual building blocks and actually the reasons why you actually need a bridge pattern. So let's discuss this example. In this example, what we have is a thread scheduler, which is an abstract thread scheduler, which has some actually extensions, which are preemptive thread scheduler and a time sliced thread scheduler. So now let's say each of the thread scheduler again has a platform specific behavior. So for example, Unix systems have their own implementation of the preemptive thread scheduler, and the Windows system have their own implementation of preemptive thread scheduler. Similarly, on the other hand, let's say for time sliced thread scheduler also we have a Unix based implementation and a Windows based implementation. So up to here it seems pretty good, this design seems pretty good, but what if, let's say we want to add one more platform support to this hierarchy? What will the code base look like? So this will look like this one. So let's say we are adding a support for Java Virtual Machine platform, and you can see that we are adding one more extension for the preemptive thread scheduler and a time sliced thread scheduler in the UML diagram. As you can see, this is starting to look pretty ugly because every time you need to add a support for a newer platform, you need to extend and give behaviors for all the thread schedulers there are actually in the hierarchy. So let's say that you have not two thread schedulers in the hierarchy, but you have 20 thread schedulers, but you have only two platforms and you want to add one more platform to the hierarchy. So what you'll have to do is to provide behavior for all the 20 thread schedulers which you already support, and this will be kind of a coding nightmare which will you never want to get into. So here in this UML diagram, as we discussed in the definition, what we are trying to do is to abstract the behavior for the thread scheduler. But what we see here is that actually the implementation for the thread scheduler is actually dependent on the platform itself, which can vary accordingly. So what bridge design pattern says, when you actually encounter these kind of issues, what you actually do is you have to decouple an abstraction, which in case is our thread scheduler. And we have to decouple the abstraction from its implementation. So we can see that our implementation for the thread scheduler is platform wise. All right. So we'll see in the next UML diagram how we can avoid this. So this is the UML diagram for the bridge design pattern. And what this UML diagram and bridge design pattern suggest is that the client will only talk to the abstraction layer, and the internal implementation which you want to vary will act as a interface where you can inject the behavior based on the implementation. So let's take a look at this example in a more deep way so that you understand the actual essence of this pattern. Okay, so if we compare this design pattern with the adapter design pattern, so adapter design pattern actually gives you a way to make things work after they are designed. But you can apply bridge pattern to the problem to make them work before they are actually implemented. Also, if you look at some of these structural design pattern like strategy pattern and bridge pattern and state pattern, all they have a common or similar solution structure where you can actually imagine the UML diagram like a handle slash body idiom. What this handle slash body idiom means, like you have a abstraction which behaves like a body for your solution, which will have all the logic on how to operate on the actual implementation, and this body will be actually talking to the client, but internally you have a handle to flip the behavior in the runtime so that you can actually have any kind of possible permutation of your combined logic. So here in our case, to implement the thread scheduler, what we need to do is we need to abstract the thread scheduler by providing an abstraction which the client will be talking to, and have a interface for the platform itself which will provide all the functional and behavioral implementation for different kinds of platform. And what we will be doing is injecting that interface in the abstraction at runtime to get different behaviors for every kind of possible combination. So this is actually pretty good. It gives you a great amount of control on how you want to actually make your inheritance hierarchy look, and it also is very manageable because every time you want to add a actual need to add a platform or a new abstraction, all you need to do is to only extend the abstraction or implement a new implementation. So every time you feel like you have a orthogonal dimension of dependencies which can exist independently and kind of have a combination between the two orthogonal hierarchy, you should go for the bridge pattern. And the way you can identify is looking at this diagram. When you see like you have abstraction which have two kinds of behaviors, and for each behavior you have certain kind of repeated behavior across the entire inheritance hierarchy. At that point of time you can actually know that here I have two orthogonal hierarchies which I can vary independently from each other. So in scenarios like this you can actually have bridge pattern applied to it. One more example people gave to explain this bridge pattern is like you have a shape which is an abstraction, and then you have an implementation level layer which is of color. So every shape is can be of red, blue, or green color, and they explain you like if you want to add a yellow color shape to the inheritance hierarchy, it will be a complete disaster. So you can also actually discuss this here. So this thread scheduler can behave like the shape, and this primitive and time search schedulers can actually behave like red, like square and rectangle. And this platform level implementation can be termed as red color square, green color square or blue color square. Similarly here also, let's say you want to add one more shape to the hierarchy. Let's say you want to add a triangle to it, and then you want to add a red triangle and a blue triangle and a green triangle. So the solution to these kind of orthogonal hierarchy problems, which have a very involved combination of this abstraction and implementation combination, what you can do is to separate out these hierarchies. So what you will have is a shape abstraction, and every kind of shape will actually extend this abstraction and give their own behavior. And on the other hand, you can actually inject an implementation which will be of color, and every color implementation can actually go and implement their own behavior in their own way. And all this abstraction will do is talk to the client class, but internally it will have a reference to the implementation which will be injected at runtime to actually flip the behavior of this abstraction as required. So this is a very nice design pattern, and I like it a lot because it gives you so much flexibility you have in their code using inheritance. So we will quickly go and try to code this shape example in Java and take a look at how this saves us from coding a hell lot of classes. So I have created a very small example which will demonstrate the usage of bridge pattern in Java. So let's look at our code and let's try to map it to the UML diagram we saw for the bridge pattern. So the first part is the client part. So I have created a client class which is named client, obviously, and this is actually where we are implementing and testing our code for the bridge pattern. So for the abstraction, what we are trying to make something abstract here, and that abstraction here is our shape class. And in the shape class, what we are doing is we are providing a shape type and an area. So the area method is actually abstract, and the subclasses will actually compute the area. Along with that, we have also a property called color, which is our implementation, which can vary from the abstraction. So if we go inside this color, this is actually an interface which provides its own behavior of filling the color. So I have created two colors, which are the red color and the green color, which simply return the color of the given object. So let's say green color returns solid green color and the red color returns solid red color. So we will be able to swap the colors from the shape abstraction independently. Now let's say how we are extending this shape abstraction into multiple different subclasses. So I have a square created out of shape which has its own side length and a way to compute the area. And similarly we have a rectangle class which have its own length and breadth, and it has its own implementation to compute the area. In the constructor of square and shape and rectangle, I'm taking the color type for the shape and actually passing it to the base abstraction, which is our shape class. And in the shape class, I have provided one method to actually set the color independently of what kind of shape we have. So if you can pass actually a color, and the color handle will actually start pointing to the new color you point to. So we'll quickly go to our client class and see how this actually lets us switch the behavior of the implementation from the abstraction at runtime. So let's go to our client class. Let me remove all this code I have already written here. So let's go ahead and quickly create a shape which is of type square, and we will pass a length of the side to it and a color type. So let's say we are passing a red color. Now to display actually the shape, what I have done is provided a method to paint the shape, which will actually display what color of the shape is. So let's quickly run this code and see what is the output of the program. So as you can see, we are seeing painting square with solid red color. So let's go ahead and create a rectangle, which is called rectangle, and we will pass length 6 and width 4 and a color type of green color. And let's say we want to print the what color is of the rectangle. So let's run this code again, and you can see how easy it is to create and vary the implementations for the abstraction. Now let's say after some time you got bored of this red color square and now you want to change it. So what we will do now is we will slightly refactor our code, and what I'll do is just copy this code here. We'll create a reference for red and green color. Let's also rename this to red color. Now instead of creating a new object every time, what you can do is reuse this red color and reuse this green color which we have already created. Since the function inside this red and green color is purely it's a pure function which is not dependent or has no state, so the only job of this function inside the red color is to paint the shape. So let's say you want to have a square which was initially of red color, but now you want to change it to a green color square. So what you can quickly do is square dot set color, and here you can actually pass the green color. And now when you do the square dot paint shape, the behavior of the class is actually changed at runtime without any code changes to the existing code. So as you saw in the UML diagram where we discussed that every time you wanted a different combination, you needed to add it across the hierarchies for the abstractions. But here, after implementing the bridge pattern, what we can do is add implementation here and inject it at runtime, and it will still behave the same. So that's what we are doing here. We are adding one more green color implementation and we are injecting it inside here. Let's say, so today we don't have any yellow color here. So what we can do is just quickly go and create a yellow color which will implement this color interface, and quickly come here and actually inject the yellow color, and without any changes your square will start accepting yellow color because it's still of type color and it only depends on the paint shape and the fill color method. So your code will completely accept the any new colors what you add as implementation of the color class, and also your older color class will be able to work with the newer abstraction. Let's say you add a triangle to the inheritance hierarchy, so it will be taking that into account. So this is how the bridge pattern works. I hope I have made you understood how it behaves. If you have any questions, you can ask it in the comments, and in the next video we will be discussing the composite structural pattern. So I'll see you in the next one. Thank you guys.